Good evening, everyone. Welcome to the February meeting for our North Texas chapters meeting for our local chapter here. Glad you all are with us here in person and online. Before we get into our speaker, first I want to say that the regional science fairs happened this past weekend. The Dallas one was on Saturday, and the Fort Worth one was yesterday. Down at UT Arlington, and they were both a success. The Dallas one was very well attended, and Shannon was very grateful to help us with the Fort Worth one on Monday. It was a lot of fun talking to the students. There were some really good projects. Makes me feel like I need to brush up on my game with everything they were doing. And our chapter was graciously donated to both events, general funds, and a special reward for the Fort Worth one. So it was great to support the students there in both Dallas and Fort Worth for it. And I say it was successful. I enjoyed it. Shannon, I hope you enjoyed it.
Yeah, it was great. I really enjoyed it. It's been a minute since I've done that, and so it was just great to talk to the students who were so enthusiastic and trying to see, oh, yay, the next generation coming up. There's hope. So, it was good. I liked it.
We're in good hands. And it was great to see all, the excitement of all the students. So that's, I guess that was the, pretty much the big thing. So as I get into the speaker, so when I asked our speaker to join us for here, I thought it'd be very topical because we just had our round of, winter weather with ice and thunder, sleet, and, everyone driving off the roads. And of course, now we'll be talking about snow. It was 90 at DFW today. So that's Texas for you. So with that, I am going to introduce Sebastian Harkema. Soon to be Dr. Sebastian Harkema. He is a PhD student at the University of Alabama in Huntsville. He's also affiliated with the NASA Sport Program at Marshall Space Flight there in Huntsville. He's been doing a lot of work on Thundersnow and working with the field campaign known as IMPACT. So it's the Investigation and Precipitation for Atlantic-Coast Threatening Snowstorms. He is a graduate. He's gotten his previous degrees at University of Central Michigan, and also just a fun tidbit because I just wanted to throw this out here that he was recently featured in National Geographic with his Thundersnow Research. So it was a really nice honor for him and for you, Sebastian. So his presentation is called "A New Era in Thundersnow Research," and Sebastian, the floor is all yours.
Okay, thank you for the kind introduction, Steve. I just also want to mention that, oh man, it's been 6 years now since I was actually a mentor under Steve back at when he was still in Oklahoma. So big shout out to him for helping me making to be where I'm at right now. So I'm going to go ahead and just share my screen. And okay, cool, you can see it. And so hopefully you can see my presentation now.
We're good.
Okay, perfect. Before I get started, I just want to let everyone know that I am getting over a slight sinus infection. So if I have a coughing fit or a sneezing fit, I am sorry in advance. So going forward, since this presentation is talking about thundersnow, I really need to talk about what is lightning and what causes lightning. So just in a very general sense, lightning results from the collisions of grapple particles, which are just really soft hail particles, ice crystals, and supercooled liquid water in the mixed phase region within the cloud structure itself. Then once these collisions actually occur, they create charge. And eventually when this charge becomes separated via like an updraft or heavy particles falling, for example, the grapple particles are a little bit heavier, so they fall. This creates a charge separation. And if this charge separation actually becomes large enough, we can potentially get a lightning discharge. And we can actually see a little bit of that charge structure itself in the actual figure that you see on the screen, where we have positive an A, negative in B and again positive in C. This is called a tripole. I'm not going to go into a whole lot of details, but it's just the general charge structure of what we see in summertime convection. Additionally, we also see it in wintertime convection, but it's slightly different. So with that in mind, really what is thundersnow? Well, in just a very general term, it's just simply lightning that coincides with snowfall at the surface. It's pretty self-explanatory. Unfortunately, it's been historically very difficult to identify thundersnow itself, owing to lightning detection efficiencies of different ground-based networks, as well as subjectivity of human errors in identifying lightning within snowfall itself. Additionally, it's also hard to identify thundersnow because this actual snow absorbs and muffles the sound of the thunder itself compared to rainfall. So it's actually pretty difficult to actually hear thundersnow itself. So going forward, historical accounts of thundersnow. So we think of thundersnow as, at least in the electrification community, as a relatively new field. Well, that's not necessarily the case. Almost 900 years ago, back in China, they actually viewed thundersnow as a precursor for military advancement. So it's pretty interesting. They've actually identified thundersnow 900 years ago, and yes, it was for different reasons, but they still were able to identify it. More recently, the first observations of Western literature of thundersnow dates back to Herschel in 1888 from the early 19th century. So that study actually came out from the UK, so it wasn't in the United States. Additionally, the vast majority of the thundersnow studies in the winter electrification studies that you'll see in the literature is mainly and primarily out of Japan. And this is just because of the feature that you see on the slide. If you're not really familiar with the Sea of Japan, it's actually just the separation between China and Japan itself. And when we have cold air moving across the Sea of Japan, it creates this these wave-like structures similar to what we have in lake effect snow. Additionally, thundersnow has been studied more in Japan just because of it's a little bit more, it has a little bit more elevation and it's a little bit more mountainous, so that we have an forced upward orographic lift as well as the convective bands of the actual Sea of Japan snowfall itself. So a little bit more recently in the United States, thundersnow didn't really become popular, quote unquote, until the late 1990s, and it all started with Schultz 1999, where they just looked at lake effect snow versus lightning and non-lightning out in Utah and the eastern Great Lakes. But I'm not really going to talk about lake effect snow, and because that's more convectively driven. For this talk, I'm going to be talking about stratiform precipitation and snowfall. So this is associated with these large expanded structures that is actually going to be occurring out in the Midwest today or tomorrow and the following days, which is going to produce potentially 20 inches of snowfall in Minneapolis and Minneapolis, St. Paul. So Moore et al. 2000 or Market et al. 2002, they actually created a climatology based on ground-based networks, and what they found is from the stratiform precipitation and snowfall and lightning initiation is they found that thundersnow is more likely to occur on the northwest and northeast side of the actual low pressure system when we're looking at this extratropical connection with actual thundersnow. And this is not really surprising considering that's where the actual snowfall is actually occurring. But when we look at the actual climatology Market et al. 2002 developed, you noticed a few things, that there's several target points, particularly out west over Utah. And this is mostly affected by orographic lift and thundersnow produced from that process. Additionally, you also have these hot spots over the Great Plains in the Midwest, and this is just associated with these extratropical cyclones traversing across the region. Additionally, you also see a maxima over the Buffalo area, and that's just because of the lake effect snow itself. So it should be mentioned that the climatology that Market developed is actually not based on lightning observations themselves. It's actually based on ground-based networks that are added into the METAR reports. So it actually has to be snowing, but then thundersnow actually has to be manually entered into the METAR reports. So over a 30-year period, they had 229 reports of thundersnow using this method. So, at that point, people are saying, oh, it's relatively rare, but that's not necessarily the case. So a lot more research has come out of the market group at the Mizzou University. And I mean, a lot of research has come out of his group. So for example, Crow et al. 2006, they actually found that thundersnow adds confidence that a extratropical cyclone actually can produce greater amounts of snowfall accumulation when thundersnow is actually occurring in the system. Unfortunately, they did not find any direct correlation between actual snowfall accumulations and thundersnow itself. At best, they determined that if thundersnow occurs somewhere nearby, we can demonstrate that the system is going to produce roughly 15 centimeters of snowfall somewhere in the vicinity of the thundersnow flash itself. So this kind of goes into the major misconception about thundersnow, particularly when we consider what we see in, for example, convective storms, where we have a lot of lightning occurring heavier precipitation. Well, that's not the case in actual snowfall itself. Or in general, thundersnow actually occurs away from the highest reflectivity and the greatest snowfall rates at the surface itself. And we can actually see that in this really fuzzy bar graph, where we have the count of thundersnow initiation with respect to the leading edge, LE, and so that's pretty much what we can see on the diagram that I drew, where the orange areas are the leading edge of these snow bands, these large snow bands itself. So what we were seeing is that thundersnow is more likely to occur on these leading edges of these heavy snowfall rates. And additionally, we can use thundersnow as a potential nowcasting tool. So if thundersnow occurs, since it's on the leading edge, we know that thundersnow is going to actually be intensifying, or snowfall rates could be potentially intensifying in the next 15 to 30 minutes. So all this is backed up in multiple studies where they found that thundersnow is more likely to occur on these southern side of these bands and on the leading edge of these snow bands on the synoptic scale itself. So now kind of going into thundersnow and tall objects. I hinted at it earlier in the presentation. Sorry. Where we have these charge structures, these positive, negative, positive charge structures in these summertime storms. And they're also relatively the same for winter storms. But as you can see on the diagram from Japan, these storms are actually relatively shallow, where cloud top heights are 6 to 8 kilometers above the surface in general. But it still holds that positive, negative, positive charge structure represented by the orange, green, orange coloration. So with that in mind, since these charge structures are actually closer to the surface, they're more likely to interact with tall objects such as skyscrapers, wind turbines, communication towers. And as a result, with that interaction with these tall objects, thundersnow and winter storms particularly are likely to initiate these thundersnow flashes. More specifically, a recent study found that towers that are taller than 400 meters are actually increasing cloud-to-ground lightning densities by a medium of 150%. So this study was actually looking at the Sears or Willis Tower in Chicago. So they found that just in these winter storms, just because the charge centers are much lower compared to summertime convection, they're more likely to initiate off these tall objects. So that's why they could be potentially dangerous if you're out in the snow and you're near tall tower itself. So I know this is not a whole lot of my research per se, but I just want to give a brief summary of what we've covered so far. So locations are determined based on the previous ground detection networks and METAR reports. And unfortunately, ground networks back in the day, back in the 90s, weren't actually very good at detecting lightning compared to what they are now. Additionally, we know that thundersnow is actually not coincident with the largest reflectivity structures itself. So therefore, we have a displacement in the actual thundersnow compared to the heaviest snowfall rates at the surface. Additionally, and connected to this, is that thundersnow is occurring on these leading edge of these snow bands, and they're more likely to actually initiate off a tall object such as wind turbines. Additionally, it provides insight into the potential increases of snowfall rates and accumulations. But again, there is no direct correlations right now for thundersnow initiation and snowfall accumulations. But on the slide, it says pre-2017. So what really actually happened in 2017? Well, fortunately, we had the launch of the GOES-R series. And on top of that GOES-R series, we have an instrument called the Geostationary Lightning Mapper. So in this slide, you can see some preliminary data of this GLM data at the bottom. And at the top of the panel, you can see just a snowfall rate product from radar as well as satellite. and represented by the blues. And in the red circle, you can see it's actually snowing over Mount Olympus. Additionally, at the same time, we can see that the lightning mapper is actually demonstrating lightning. So if we have snowfall according to this product and lightning as a part of another product, we can objectively and subjectively say that this is thundersnow. Additionally, it should be mentioned that not many people actually see this image, and this is probably the first detection of a GLM thundersnow flash. So that's pretty much what brought my interest into thundersnow, so kind of keep that in mind. So what is the geostationary lightning mapper? Well, as I mentioned, it's part of the GOES-R series. I'm not going to go into a whole lot of detail about it. Just know that it's a radiometer that detects at a narrow 1 nanometer band centered on the 774 wavelength. It's based on 3 different components: events, groups, and flashes, where events are the base pixel level. The pixel level data of the GLM, where then they're grouped into groups, and eventually, if they're spatially correlated in time and space, these groups are merged into what we call a flash. So the GLM was actually designed to have a total lightning detection efficiency of approximately 70% at nadir. And unfortunately, a lot of studies have shown that this is being generous for what the instrument can actually do. So something that is actually beneficial to society and forecasters is that the GLM has provided a really great insight of the horizontal extent of lightning, which means that it can actually have associated with it multiple ground-based lightning flashes associated with a single GLM flash. So going forward is, how am I personally identifying thundersnow in GLM? Well, I kind of hinted at it earlier. As part of my master's, I developed an algorithm that can objectively identify these thundersnow flashes from the GLM based on the overlap of GLM data represented by the white circle and the lightning data that you're seeing over Long Island. And it's overlapped on this, what it's called the merged snowfall rate product. So it's a derived product that can estimate the surface snowfall rates from radar as well as satellite data itself. So I'm just looking for the overlap of the 2 data sets, and I'm just saying, okay, if they're overlapped, they're going to be thundersnow. That's just what I defined it as. So I'm not saying, if I hear thunder, I'm not really hearing the thunder. More specifically, it should be called a lightning snow detection algorithm. But, historically, we have to keep it with thundersnow. So with this in mind, as part of my master's thesis, again, I collected a bunch of cases from January to April 2018, a total of 21 heavy snowfall cases that were associated with these extratropical cyclones that traversed across the United States. And of those 21 cases that I collected during this time frame, 18 of them actually produced at least 1 thundersnow flash. So from that in mind, my algorithm was able to pick up roughly 53,000 potential thundersnow flashes that were potentially identified by the GLM. And after some quantitative analysis and some kind of quality control, I whittled it down to about 2,200 flashes were classified as thundersnow. And we can actually see that in the orange dots compared to the blue dots, where the blue dots are just where my algorithm was just saying, okay, this could be thundersnow, where the orange dots are saying, I'm pretty confident that this is thundersnow. And the black dots you're seeing is just METAR reports of thundersnow during this same time frame. So from the market paper that in the climatology, we can see that, well, there's not a whole lot of thundersnow based on the METAR reports, but from the GLM perspective, we can see that there's a lot more thundersnow than what we can previously, just in this 4-month period. So with that in mind, is what can we say about thundersnow? Why is it important from a GLM perspective? Well, I just gave some really brief statistics. I'm not going to go into it too much, just because it might be, it's interesting, but it's not overly interesting. But the important part is, when looking at the actual slide, and the image on the slide is that these thundersnow flashes in the orange are actually in the upper ends of the flash energy per flash area spectrum. So what this really means is that thundersnow flashes are brighter per area compared to non-thundersnow flashes. And this could be a lot of things. It could be associated with the fact that these lightning flashes are just generally large, so they're just brighter compared to non-thundersnow flashes that are occurred in, say, supercells. Or it could be just because the actual clouds themselves are much shallower compared to summertime convection, so more light is coming out of the cloud top itself. But more interestingly, from a statistical standpoint, the mean thundersnow flash that I collected as part of my master's thesis were between the 90th and the 99th percentiles for brightness as well as duration. So thundersnow flashes are statistically significantly larger and longer, but they're also brighter compared to other flashes that GLM actually is being able to detect. Additionally, approximately 14% of these thundersnow flashes that I collected or identified were actually associated with these tall human-built objects like wind turbines and antenna. But it should be mentioned that this percentage is probably a little bit higher. It's probably closer to 26 to 35%, just because the GLM actually can have multiple ground-based network flashes within a single GLM flash itself. So now going into the actual quantitative analysis of what we can see and what we can find regarding thundersnow to potentially better forecasting of, for example, snow to liquid ratios. So this actual demonstration is a snow to liquid ratio bar plot. It's actually a gamma distribution where we can see the peak of this distribution is about 8. So that means that if we melt down 8 inches of snowfall, we're going to have 1 inch of liquid equivalent. So now I broke this actual plot down into actual box and whisker plots based on different GLM categories. And you'll see this in the different slides as well, where the first column is representing GLM flashes that had no ground-based network connections. The second is where these flashes, GLM flashes, actually had ground-based support. Then I broke that category up into intercloud flashes or cloud-cloud flashes. Then I eventually broke that up even further to include tower flashes or cloud-to-ground flashes that are associated with towers and cloud-to-ground flashes that were not associated with towers. So what you can see on the actual diagrams is that these tower flashes actually are associated with a slightly higher snow to liquid ratio. So what that really represents is that these flashes associated with towers actually are associated with more liquid water itself. So these are just suggesting that these particles are a little bit wetter, they're a little bit heavier, so just stuff like that. Now with regards to actual snowfall rates, again, this demonstrates that thundersnow is not occurring in the heavy snowfall rates as demonstrated by the gamma distribution again. More specifically, we find that thundersnow is actually occurring in snowfall rates less than 1 inch per hour. And again, I should mention that this is for the stratiform thundersnow flashes that I collected. This eliminates a lot of elevated convection that is associated with thundersnow, for example, in Texas and Oklahoma. And I'll demonstrate that and show that a little bit later in the presentation. So if we actually look at the estimated snowfall rates from the actual data itself, we can see that when GLM is associated with ground-based networks in the second column, box and whisker plot, is that these specific flashes are actually associated with higher snowfall rates compared to GLM flashes that are not associated with any NLTN flashes itself. So that really suggests that, at this time frame, that GLM is actually able to identify and detect thundersnow flashes better than the ground-based networks themselves. And additionally, if we look at tower flashes, they're occurring in a slightly higher snowfall rate. And this is, again, associated with higher liquid water content that I mentioned in the previous image. Now, looking at actual snowfall accumulations, because a lot of people have suggested in the past that if we have a thundersnow flash, we can expect a lot of snowfall. Well, that might be true, but there's really no strong correlation between snowfall accumulation and thundersnow occurrence. If we look at the actual diagrams, we can see that the mean and median snowfall accumulation for thundersnow flash is about 10 inches. So that's according to what we see in literature as well, so it matches up. When we look at the different categories in the box and whisker plots, is that a lot of the flashes are pretty uniform. So again, that really suggests that there's not a whole lot of correlation between snowfall accumulation and lightning occurrence, which is really not that surprising if you really think about it, because lightning initiation is more on the really small scales with the particles within the cloud, and snowfall accumulation is over a long period of time, and it's on a more, several hour time period, where lightning initiation is on the order of nanoseconds. So that's what probably explains why we don't have a really clear correlation between snowfall accumulation and lightning occurrence in snowfall. So these polar plots pretty much demonstrate the same thing for thundersnow and the heavy snowfall rates. So I'm just going to have you really focus on panel A and on the left side of the plot. And this actually demonstrates the polar plot and the frequency of heavy snowfall rates greater than 1.75 inches per hour for all thunder snow flashes that were detected by the GLM between January and April 2018. So what you're going to see, if we have the center of the plot is where the actual thunder snow initiation occurred, we can actually see that there's actually a spatial there's a spatial difference between the actual location of the thunder snow in the white circle and what we see in the heaviest snowfall rates, where, you know, on average, they're between 50 and 100 kilometers away from the actual thunder snow initiation itself. You know, additionally, we can see that we have even higher probabilities even further away. And these are skewed by just different events over time, just because this is a relatively small study of 2,200 flashes over a small period of time itself. So these early GLM thundersnow observations, in a summary up to this point, thundersnow is actually much more common than what we previously have thought from literature. These thundersnow flashes that were detected by the GLM are statistically larger, they're brighter, and they last longer compared to all the other lightning flashes that GLM is observing. And this is likely just associated with just the general physics, where in these wintertime systems, we have weaker ascent in the vertical motions, which means that it takes longer to generate charge. From that, this slower charge generation creates these larger flashes. Additionally, 10+% of these thundersnow flashes were actually associated with tall objects, whether they were communication towers, wind turbines, or buildings. And additionally, as you saw on the previous slide, there's a spatial offset between the actual occurrence of the location of these thundersnow flashes and the heaviest snowfall rates themselves when associated with the extratropical cyclones. And lastly, for this slide, is there's really still no direct correlation between the total storm snowfall accumulations and thundersnow themselves. That's just breaking that misconception from previous studies. So now moving forward as part of my PhD, I wanted to look at, well, what's next? What can I do next? Well, the next thing would be looking at satellite imagery. That's been kind of my goal since day one. So so the imagery that you're seeing on the panel on the top is actually a large thundersnow outbreak that occurred in early to mid-April 2019. This actual imagery is called the day cloud phase distinction RGB, and it's derived from the GOES-R satellite, or GOES-East. And the actual imagery can be described looking at RGB interpretation at the figure at the bottom. So more specifically, I'm just going to point you to number 1 and the number 2 and 4 regions, where number 1 is represented by these low-level clouds that are almost all water droplets. So at this point, we don't have any ice in these clouds itself. And eventually, when they start to propagate and grow in the vertical, we get more ice clouds associated with glaciating clouds, represented by more green color by number 2. And eventually, number 4, where we have really these high, thick clouds that are probably considered stratocumulus or nimbostratus itself. So as part of my PhD, I expanded this research, and from what I did in my master's, and I expanded it into 2019. And from there, I looked at 10 different ABI channels, or the Advanced Baseline Imager, as well as these 4 different multispectral RGBs. Example is the day cloud phase distinction RGB, for approximately 17,000 GLM flashes that were classified as thundersnow. So I've really expanded the actual output for these cases compared to what I did in my master's. So previous literature has really shown, at least in summertime convection in Florida, is that we see very distinct patterns in particularly the day cloud phase distinction RGB for forecasting cloud-to-ground lightning. So what forecasters out in Tallahassee noticed is that this imagery that you're seeing on the slides actually transitioned from a blue water cloud to more of a yellow-green ice cloud themselves prior to thundersnow, or prior to lightning initiation in summertime convection. So with that in mind, I wanted to try to understand this process to see if it's true for thundersnow flashes. With the understanding this is going to take a lot longer, just because the vertical motions associated with these winter storms are actually much weaker compared to summertime convection. So I have to track cloud features for a much longer time frame and over a much longer distance compared to summertime convection over Florida. And that created a little bit of a problem. So to try to solve this problem, I used another product called the Derived Motion Wind Vectors. This is another GOES-R satellite-derived product, and it's pretty much just estimating upper-level winds from the ABI from satellite imagery. So what I did is, if you look at the diagram, I have a lightning flash at 11:45 UTC. I use the derived motion winds in the orange, and I invert them to track the cloud feature back in time. So another 15 minutes. So at 15 minutes and another 15 minutes, another 15 minutes, to eventually at 10:45 UTC. And this is just an example of how I kind of just hard-coded a way to track cloud features, just because the distinct motions of these extratropical cyclones can be very difficult over particularly a 2-hour period of time. So I'm going to show an animation in this slide, and it's going to just show you how the algorithm is actually tracking cloud features. What you're going to see on the map is a red dot at T-2 hours prior to lightning initiation. And as it traverses in time, you're going to see that a lightning initiation is occurring at T-0 hours. Additionally, using this algorithm, I'm able to characterize how these imageries change in color. So at T-120 minutes prior to lightning initiation, during this time frame and for this specific flash, it's kind of more of an olive color, but eventually it becomes more of a tan color. And this really just represents, if it's going to play, hopefully. Oh, please play. Oh, I guess it's not going to play. Sorry about that. That's kind of disappointing, especially with later animations. But it just shows you as it's tracking the time that the actual color of this specific imagery changes with time. So with this in mind, I want to keep in mind this linear pattern that you're seeing going from 120 minutes to 0 minutes in the next slide, in the next imagery, just because it's a little difficult to see. But what you're going to generally see is that at 2 hours prior to thundersnow initiation, we have a lot of really bright blue cyan colors. And as we get closer to lightning initiation and thundersnow, these yellows and green colors are actually the vast majority of the colors in this specific day cloud phase distinction RGB. So this really confirms the idea that these clouds are starting out as water clouds, they're glaciating and becoming icy, and eventually they become almost all ice in the mixed phase region prior to the lightning initiation. So this really just benefits with understanding of forecasting for thundersnow initiation from a satellite perspective. I've also looked at different satellite imagery products. And one thing I did find is that eventually as the cloud feature was tracked over time, we actually noticed that the actual upper levels became drier over time prior to lightning initiation. So this really kind of just steepens the mid to level lapse rates, which actually makes this environment a little bit more unstable itself. So this is potentially why we have lightning initiation in the regions we do, just because this upper level dry air mass actually steepens the mid to upper level lapse rates, which makes the environment more unstable. So that kind of goes into the second chapter of my PhD, looking at the NASA Impact Field campaign. While this, so far the campaign has yet to actually measure lightning initiation and snowfall, we have still collected pretty good observations from the Lightning Instrument Package, or LIP. It's just an electric field mill that can measure the electric fields above these cloud feature tops at about 20 kilometers altitude. And it's because it's on board the NASA ER2, which is pretty much just a glider, and it's just an old spy plane that's been converted over for NASA for these type of field campaigns itself. So with this in mind, I wanted to personally try to investigate the importance of the supercooled liquid water and the grapple within these electrified snowstorms, just because historically in the literature it said that these two ingredients are the most important ingredients for electrification processes. Schultz et al. 2022 actually were the first to use some of these electric field measurements, and they found that they had electric fields of about 70 volts per meter above these non-lightning producing winter storms, particularly for the February 7th, 2020 science flight itself. I'm really sorry about including equations. I didn't really want to include it, but it's kind of important. So from a scientific standpoint, we have accretion, which is just ice crystals growing via the collection of this supercooled liquid water. And it's really necessary for the traditional quote-unquote non-inductive charging, which is pretty much the idea that we have grapple particles, ice crystals, and supercooled liquid water colliding with each other in the actual mixed phase environment. And that's what really causes the electrification within the cloud structure. Whereas diffusion is the growth of these ice crystals via water vapor itself. So if we think of diffusion, historically we think of these really pristine, pretty ice crystals, for example, really pretty dendrites, and that's in a more non-rhyming environment. So I just really set these two growth equations equal to each other, and as you can see on the slide, and I solved for M, which is just the liquid water content. So when I do that and shuffle around the terms, I eventually get M, which is now representing a liquid water content threshold that really separates potentially charge-separated regions associated with non-inductive charging, associated with these ice particles, these grapple particles in supercooled liquid water, and ice-ice collisions in a non-rhyming environment associated with potentially only ice crystals and very little supercooled liquid water. So what you're going to notice is that M and SI, or the supersaturation with respective ice, they're linear. It has a linear relationship, and we can actually see this linear relationship where if we have a observed liquid water content on the y-axis, if it's above the line, this linear line that you see, it's actually going to be associated with accretion. So therefore, we're going to have more rhyming particles associated with the non-inductive charging itself. But in contrast, if we have actual observations of liquid water content below this linear line, it's going to be more associated with diffusion, which is going to be more associated with actual pristine ice crystals and really pretty ice crystals that you're going to see later in the slides. So this is kind of just what we came up with in a very theoretical model sense, where we actually have accretion at the same time frame represented by this deviation. So blue, the darker the blues, the higher confidence that we have its accretion associated with higher liquid water contents, and it's actually associated with this traditional non-inductive charging with grapple particles. But in contrast, towards the highest electrification, represented by the black lines, we actually see diffusion, and the oranges and yellows are having highest confidence for these simulated particles that were from the NASA Impacts Field campaign. So what this really suggests that the highest electrification represented by the black lines is actually more likely to occur, at least in this time frame, in a more pristine ice crystal environment. And this is just based on the microphysics of the aircraft data itself. Now looking at actual particle observations, during the time frame of when the model was suggesting more accretion associated with heavily rhymed particles, we can actually see it matches fairly well with what we see from the model, where the particles are, you can't really tell what they are. Yes, they're ice crystals, but they're very heavily rhymed. They're associated with higher liquid water contents themselves. But in contrast, if we look at the second image, yes, there's smaller ice crystals associated with shattering, but you can still see through these ice crystals. So that's why it adds confidence that the ice crystals themselves, if they're falling at a specific fall speed, they're actually associated with more of a diffusion growth rate itself. So with this in mind, in the summary for this particular slide is the strongest electric fields are actually associated with these low liquid water content environments and diffusion growth rate regimes, at least for the February 7th case from the NASA Impacts Field campaign. So now kind of going back into where I'm going forward, what I'm doing currently. So right now I'm using the Weather Research and Forecasting Electrification, or WARF-ELECT. And this actual specific parameterization actually explicitly resolves hydrometeor charge, electric field, and lightning discharges itself. Previous studies have used this simulation and whatnot to actually simulate successively lightning discharges in summertime convection. Unfortunately, these studies have actually had a very difficult time simulating thundersnow. So that's where I come in. I wanted to specifically resolve thundersnow using this model and parameterization. So what you're going to see now on the slide is if we look at actual observations in the top panel where we have radar reflectivity, and in the black oval is we have these blue and pinks, and that's actually thundersnow from the GLM. But from the model perspective and the two bottom panels, you have simulated radar reflectivity. It matches fairly well with what we see in observations. But more specifically, if you look at the bottom panel in the black oval, you can really see these really faint blue purple specks. And this is actually thundersnow that is successfully simulated using this electrification parameterization. So for the first time ever, this is the first lightning initiation in thundersnow explicitly. So no one's done this before. No one's really examined this before. So what you're seeing is on leading edge research. So now we're just going to be comparing the bulk comparison of lightning initiation from the GLM and the model output for the April case from 2019 that I mentioned earlier in the presentation. So I just kind of time integrated all the GLM observations when they're gridded over a period of time for the event and compared it to what we see in the actual model. So what you're going to see is the darker colors represent smaller flashes, whereas the middle panel represents flash extent density. So it's pretty much the spatial extent of flashes and how many of them occur over a period of time. So you can see that these overlap of small flashes in the darks actually correspond really spatially well with what we see in the pinks in the middle panel. So these are a lot of small flashes occurring a lot over a period of time. And in contrast, if we look in Wisconsin, where we have more of a lighter blues and greens, so these are actually larger flashes, but if we look at the flash rates themselves in the bottom panel, they're less frequent in nature. So that corresponds well with what we see in literature. So GLM is actually doing a pretty good job from this perspective. Now, from the actual model perspective, in the bottom panel, I'm looking at maximum electric field that is simulated from the actual model itself. So it can be used as a proxy for potential lightning initiation. So think of it as these darker purples that you're seeing in the bottom panel as locations more favorable for thundersnow initiation. And the blue outline just represents the actual outline of where GLM is suggesting thundersnow itself. Now, the only downside with this type of simulation is that I noted in earlier in the presentation that thundersnow is associated with towers more often than not. And unfortunately, this actual parameterization does not simulate tower-initiated flashes. So we're going to have automatically differences between observations and the model itself. So what we see from the actual parameterization that we do have individual areas, roughly 1,100 of them, over the duration of the simulation. The actual model suggests that there's about 2,800 inter-cloud flashes, as well as 200 cloud-to-ground flashes. Hopefully the video plays this time. No, I guess, sorry about the video, it's not working, but it's pretty much a good it's a time frame of showing how the model actually is handling this electrification processes and how it goes with time. So it pretty much demonstrates as these snowfall is actually intensifying, we can actually see these thunder snow flashes actually intensifying. But if we actually look at the model observations where we have these blues, they're actually associated, that's the actual output for thunder snow, how I'm defining thunder snow in the model. So we can see that when we compare to the observations in the really kind of chunky black blob regions, it's actually matching really well. But unfortunately, the WRF output is every 5 minutes, and it's explicitly resolving lightning every 5 seconds. So what you're seeing is a really snapshot in time every 5 seconds accumulated over the course of 2 days, where the GLM is actually observing lightning every 2 milliseconds. But it's over the course of the 24-hour or 48-hour time frame. So we have that spatial extent difference, unfortunately, between the model and the actual observations, unfortunately. Let's see. So kind of moving forward, this is really kind of something that I've been working on as a side project, potentially predicting lightning using radar. This might sound kind of magical in some way, but there is some foundations understanding lightning initiation for using radar observations, particularly using the differential reflectivity, or ZDR, to anticipate electrification and lightning through a feature called ZDR depolarization streaks. So you can actually see these depolarization streaks in the actual bottom panel, where we're looking at differential reflectivity, and we have these streaking patterns in the radial. So these streaking patterns are actually caused when we have a large enough electric field interacting with ice crystals. So these ice crystals eventually align with the electric field, and as a result of the ice crystals aligning with the electric field, these cause these strange radial streaks in the actual radar data themselves. So with that in mind, we can potentially use these differential reflectivity ZDR streaks themselves to potentially anticipate lightning initiation initiation in stratiform regions. So as part of this side project, I tried to develop an algorithm that can actually try to identify these type of features. And if we look at, the raw differential reflectivity in the top right panel, we can see that if you look closely, there are these streaking patterns in the actual data. And the plus and minus signs represent lightning initiation that's occurring within plus or minus 10 minutes of the actual radar image that you see on the slide. I'm not going to go into how the algorithm works since it's still pretty experimental, and my mentors want to keep it kind of hush-hush, so they don't really know that I'm showing this slide at all. So kind of be forewarned. But my algorithm is able to pick up on the region of where it's objectively identifying these ZDR depolarization streaks. And what you can see is the algorithm really matches up well with what we see as far as the lightning initiation locations themselves. So that adds really confidence that these depolarization streaks that the algorithm is identifying matches well with what we're seeing in the lightning observations. So we could potentially use this algorithm as a way to anticipate lightning if these depolarization streaks are identified in the actual radar data themselves. So, as part of this talk, I wanted to talk about your recent Thundersnow event that occurred in late January to early February. As a brief overview, what we can see in the surface map that you can see, you had an Arctic front pass through the region, bringing really cold temperatures. As part of this, a lot of the thundersnow that Texas has, as well as Oklahoma, it's actually associated with these elevated convection as associated on the backside of these Arctic fronts. Additionally, we have southwesterly flow aloft. So this is what really kind of just brings up the actual elevated convection. During this time frame from January 31st to February 2nd, the GLM actually identified 1,700 flashes that were classified as thundersleet and thundersnow. And you can actually see this in the bottom figure, looking at the map, where we have a lot of flashes represented by the blues, reds, and blacks over Oklahoma and Texas. Additionally, we have a few thundersnow flashes occurring off the coast of Lake Erie during this time frame. Interestingly, during this time frame, the largest flash that GLM actually detected for this event was about twice the size of Houston, and this actual same flash was associated or lasted about 1.25 seconds. So it was a fairly large flash if we think about it, and it lasted pretty long. Unfortunately, these, as it's related to elevated convection, these flashes are still relatively small compared to larger thundersnow flashes that are associated with these synoptic scale snow bands. So with this in mind, and unfortunately this animation is not going to play, but it's pretty much a demonstration of how the snowfall rates progress with time, and it's showing the thundersnow flashes that you actually observed in Texas. So sorry about the animations and videos not playing. I'm happy to take any questions.
All right, thank you, and no worries about technical difficulties. We all have them, so we appreciate the presentation. Is there any questions, either online or here in the room? I'll go ahead and ask one here. So the first half of the research here, what was most surprising, given that a lot of the findings that you had pretty much debunked everything that was previously written in the literature?
Yeah, honestly, it was that everything that I have done has been kind of groundbreaking when it comes to thundersnow. Because, for example, Patrick Market, which I referenced a lot of his papers in the past, he was the foundation or the person that did a lot of thundersnow research out of Mizzou. And the fact that I confirmed or debunked a lot of his research is kind of really surprising. And that's mainly potentially because I'm just looking at better lightning detection instruments where he used ground-based networks that were based on human subjectivity, saying, oh, it's snowing and I hear thunder and I see lightning. Where my method is looking at from looking downwards, from the cloud structure down, using the GLM. So it's just interesting to know that thundersnow is a lot more common than what we think. And, a lot of thundersnow flashes occur at night when people are sleeping. So the fact that, the snow actually muffles the thunder a little bit, or people hear it and they're like, oh, it's just a car driving by, for example. So it's just everything about Thundersnow is interesting, and I'm hoping to continue to work with it. I really hope that answers your question.
Yeah, that's right. Anyone questions? I guess I'll ask one more here. Correct me if I'm wrong. Most of this work dealt with cloud-to-ground strikes. Yes.
A lot of this work is associated with, yes, cloud-to-ground strikes, but the vast majority of the it's just, from a human safety perspective, I focused on a lot on cloud-to-ground lightning, just because of the charge structure on these winter storms is closer to the surface. So it can potentially cause more harm and infrastructure damage, just because the charge structure itself is lower to the ground.
Okay. I was just curious, what kind of mix of cloud to ground versus intra-cloud are there with these?
Yeah, that's still a lot of, honestly, there's no good way to discriminate the potential for a cloud to ground flash compared to a intra-cloud flash. A lot of it's just based on how the charge is transferred to the surface. So for example, if it's snowing very lightly, if I go back to the actual slide that had the snowfall rates, let's see. If we look at the snowfall rates, is that these actual cloud to ground flashes in the bottom or the right two box and whisker plots, they're actually associated with higher snowfall rates compared to intra-cloud flashes by themselves. And my hypothesis right now is these CG flashes are actually associated with higher snowfall rates just because these charged particles are making it faster to the surface more often. So therefore, the lightning can follow these ice crystals themselves closer to the surface compared to intra-cloud flashes themselves. So that's why we potentially see this differentiation in statistical significance compared to CG and IC flashes from a snowfall rate perspective themselves.
Okay, cool. Thank you. Is there anyone else online or?
Steve, I have a question. So Sebastian, you said that there was no correlation between basically the convective snowfall or having, lightning associated with the higher snowfall rates. But I guess I'm curious, would you be looking into maybe more of a smaller geographic areas within the U.S.? Because at least just as a casual observer in North Texas, we tend to get those heavier accumulations when there is convection, or we do see the thunder sleet or thunder snow. And so it's just, but again, obviously it's a casual observation, but that tends to be the case, at least from for us. Otherwise they're usually live, and then when you do get that thunder or the lightning, you're like, oh yeah, it is definitely associated with heavier rates.
Yeah, so you're right. The observations support what you just said. As I mentioned, Texas, you guys get a lot of elevated convection, and it's actually associated with these higher snowfall rates and sleet events, and it's all associated with this elevated convection, which is associated with these higher precipitation rates. So this is just a very general sense, but to bring it back to your questions, I have not looked at specific geographical regions, just because my research just more associated with the broad aspects of thundersnow itself. So, it's a good question to compare potentially thundersnow events and thundersleet events in Texas, for example, compared to the upper Great Plains, where you're likely to see statistical differences between these lightning flashes and snowfall compared to Texas and compared to Minnesota.
Yeah.
So it's definitely worth investigating. It's just my research has looked at the broad aspects just because a lot of this data set is new. So you need to keep it broad just because it's relatively new research, and you can't get narrowed down into the nitty-gritty details of case studies.
I was going to say, I think every time you probably have 14 different areas that you could probably research in more depth. I mean, I think it's hard to keep it at a high level or without adding scope creep to your dissertation. So.
Yeah. Sebastian, thank you again for this fantastic talk, and keep blazing the trail, man, in this field. And so with that, I'll go ahead and start wrapping up some business here. First, Sebastian, I will get with you tomorrow or whenever I might have working internet in house, and I will get you an Amazon gift card as a thank you for presenting with us.
Okay, thank you so much, and thank you for having me. It's always good to talk about Thundersnow. I know it's especially with the event that you guys just had, and it was really impressive. I was following along with the live stream data, and I was actually really impressed by the amount of thundersnow flashes that you guys did have in Texas.
Yeah, it was really cool for us to experience on the ground.
I try not to geek out too much. We're like, oh my God.
Dave, Stanley, I don't know if you have any chapter business that you want to cover. I don't know if Greg is online. Dave, anything on your end?
We do not. Nope, I do not have anything.
Okay, sounds good. So with that, the next meeting will be the 21st of March. I know usually we do the second Tuesday of the month, but we'll be moving into the third one for some personal reasons on my end. And with that, this meeting is adjourned, and thank you all very much for attending.